Hello and welcome to classification. Let me get something started here. Let's go ahead and apologies, little discombobulated. Go ahead and share my desktop on the off chance someone joins. We are in WebEx as well. So welcome to a revisiting of Module 6. Sorry for the interruption. Revisiting Module 6 primarily because that's where you are. So we'll go ahead and jump into that, and I'll do this in a bit more of an informal way. And do a few rabbit trails where it makes sense. So Module 6 is around the classification of or the comparison of classification results. So the idea is to be able to talk about when a model is doing well and when it isn't. So the competency is around compare various classification and analytical models, and then evaluate model comparison problem. So how do you know what model is good and what model isn't? And then employ the test of potentially use a statistical significance test to determine which models are better than another. The reality is most of the time you don't really need a test to be able to tell. You're going to go for the model that has the best accuracy or recall or whatever the needs are, not necessarily go to the trouble of doing a statistical test to determine which one is significantly better than the other, and significantly being statistically significant. So, but the idea is that you do want to be able to use the receiving operator characteristic under the area under that curve. That's one of the key ways that is often used to determine the better model. And then measure training time, robustness, interpretability, and scalability of each model. So lots of stuff there. Models, if it takes forever to train, and especially if you have to train fairly frequently, that can become problematic. Also, the time for a model to determine its result, it needs to be very fast. So if you have something that is not very fast, then if it's slower than the window of opportunity to make either decision or to return a result, then it doesn't really matter. So they have to be fast enough to do whatever needs to be done, but yet they need to be good enough to be reliable and useful. Robust and be able to handle things that it hasn't seen before, and you need to be able to understand what it's doing and why it's doing it, and it needs to be able to be scalable to handle both in terms of volume of requests being sent to it and also the amount of data that's associated with each determination to make sure that that's an appropriate size. So whenever we talk about classification comparison, what is it? That's always a great question to ask about anything, and it's a way of figuring out what is best, and best is part of the problem. You got to figure out what best means. So the best model is the one which returns the appropriate results based upon the situation you're in, and this is what you're going to be doing to figure out which one of these is better, A or B. And you want to pick the one that meets the business need as well as is the best as far as in terms of the various statistical measures you may be gathering about it. Why do you want to use it? Well, you want to find the best classification, and as I mentioned, know what best means so that you can get the best performance result or whatever out of your experience. The common approaches are going to be things like looking at accuracy, recall, looking at the confusion matrix, area under the curve, things we've been talking about. You may use statistical methods, t-test, and so on, although that's not all that common. And you're likely going to be using some form of a framework, and you may be moving into things like AutoML as well, where you define the characteristic of what is good and what is best and so on, and then optimize accordingly in maybe even a programmatic way. So when we talk about comparing metrics, you want to consider the model scores and determine what good looks like. You may want to have a weighted formula depending upon if a false negative is really bad, then maybe you want to adjust your determination of what it is. It's not even close. All right, I'll leave it as it was. Yeah, this is characteristics. It's not quite right. I need to fix it later. So the basically these are commonly used. MARI is ROC and AUC, probably the most commonly used. And these type of metrics are often used in things like I mentioned of AutoML, automatic machine learning, where it goes out and basically tries a ton of different models for you to determine which one is the best. And not only a lot of different models, but it potentially does some tweaking of those hyperparameters that control the behavior of a model as well. Whenever we talk about trusting a model, there's kind of a pyramid here that we can talk about, which is around the transparency. You need to be able to know why it's doing what it's doing and be able to explain that to somebody else, be able to interpret the results and interpret the process of reaching the results, and make sure that it's consistent as well. You don't want something that ever so often is just randomly horrible. You need to understand why it does well, and when it doesn't do well, you need to understand that as well. There's also a level of accountability involved here where you expect things like privacy, security, safety, certainty, robustness, and reliability. And then models should be fair. There shouldn't be any sort of bias built into them, certainly not purposely, but even by accident, having exposed it perhaps to the model training to biased data. So sometimes you want to address bias by eliminating certain parameters from your model. So unless there is a compelling reason, things like race, national origin, probably don't belong in most models, right? Because it has the potential of being biased based upon those characteristics. So we have to ensure that our models are fair, and fair being that they're equitable in nature, and that they are inclusive, and so on. There's other factors that you'll want to consider whenever you talk about evaluation of a model. Things like how fast is it? If it's fantastic but it takes too long to run, it doesn't matter. So it needs to be reasonably fast within the time frame that you have to do it. And also there's a cost effectiveness aspect of it as well. If it's incredibly fast but incredibly expensive to run it that fast, then it may not be viable as well. It needs to be relatively flexible in nature, so it can't be terribly fragile and terribly rigid. It needs to be able to generalize well to things it's not seen before. It needs to be robust, handling things that are noisy in nature, scalable, as we mentioned previously, interpretability, so that I can understand what it's doing. So those are all elements that go into consideration whenever you're talking about evaluating a model. And the concepts here are, it's not as simple as just a single number. You may want to consider lots of different values or approaches. So there's a common pattern that you'll see, and you should have already kind of seen it and noticed it and may have even learned it formally, but it's this holdout method, which is the idea that you have a test, a train, and a validation set of data. The kind of key concept here is that whenever you're evaluating your model, you don't want it to be doing so on data that it has previously seen, because it should do quite well if you show it the second time to a piece of data. So if I take it to the extreme, I train it on one data set, and then I run that same data set through it to test it. If I don't get a very high score, that's an indication that perhaps the parameters aren't all that well adjusted, or maybe it's not a good fit for the data. But it, in theory, should do very, very well the second time it sees something, especially the entire set of data. So to kind of alleviate that, there's typically a split that occurs where you take your test set and you pull it off from the training, from the original data set, and hold it in isolation. You hold it back. And it's things that aren't seen by the algorithm until you're actually evaluating their score. And then you may take that training set and split it again, and then create essentially a validation set. The validation set is used to essentially tune the hyperparameters within the data set. So you may adjust the values based upon like how many, whatever setting it might be, beam width or something. You may want to use a validation set as a way to determine if it was good or not. Similar concept to a test set, except that it's used to tune the hyperparameters or the parameters inside of the model. And so that's a common pattern you'll see. Hopefully you've identified it. You'll see it in pretty much all domains of both machine learning and artificial intelligence. We do very similar things when we're talking about language processing as well. So a common pattern. Moving on to deliverable 6, we'll talk about it briefly. I'll try not to give too much of it away, although keep in mind if I show code, don't assume that my code is grade A code. It may be code that was back of napkin sort of code to ensure that maybe we've got good data. Maybe there's nothing terribly wrong with our data set. So kind of keep that in mind. So the data set that you're dealing with deals with radars. So it's based upon this Ionosphere Research is the company that you're supposedly working for now. And you're asked to basically use these, 5 or so different classification approaches to determine basically which one is doing the best. So imagine that this is your job. You're working for a company that deals with radar. You want to be able to determine the difference between good and bad pulses and be able to predict them with a high degree of accuracy. So which one of those models is going to deliver the best results? And so your instructions kind of fairly straightforward. You make sure your library is available, as we always do. You read the CSV into a pandas data frame so that you can then use scikit-learn to actually do some work with it. You do some data exploration, maybe do some data cleansing along the way. Then you're going to split, in this case only for training and test. You don't necessarily do a validation set, although it probably wouldn't be a horrible idea, but certainly is not required. Then you're going to build a pipeline that basically does 5 different types of classification, or 4, 1, 2, 3, 5 because we do the rule induction down on step 7. And then for each one of those classifiers, you basically will obviously create an instance of it. You'll train it. You'll do some prediction. Then you'll compute the score and confusion matrix and the area under the receiving curve. And then basically for the rule-based approach, you'll do the induction to produce the rules, to produce a classifier, use that classifier to predict the first 75 data instances, compute your accuracy, AUC, and confusion matrix, compare it with all 5. So basically take a look at all 5 of them together, and then perform some clustering using k-means, varying the number of clusters and the number of iterations for each to perform of the performance metrics, adjusted RAND index, homogeneity, and v-measure. So those are your instructions. What you're going to turn in, a description, basically a report that includes a description of the algorithm used. So talk about both the high level, you did this for 5 different algorithms, and then also a brief discussion of what each one of those algorithms, kind of how they work. Not a huge amount of detail, but a brief brushing of the material. And then the results of your data exploration, a table for the supervised learning, so the non-clustering stuff, containing the performance metrics of each of those 5 classifiers. Inside of that table include the score, the area under the ROC curve, and an explanation of how these metrics could affect the result. And then a comparison of the confusion matrix of each of the classifiers. For unsupervised learning, a table containing the adjusted RAND index, homogeneity, and the v-measures versus the number of clusters and the number of iterations. And then a comparison of the training time of each algorithm. So you'll want to have a measure of capturing start and stop of those so that you can produce a training time if it's not available to you out of the box. Talking a bit about the data set itself, it comes from a while back as well, and it was in Goose Bay. Basically there was a set of 16 high frequency antennas that transmitted with 6.4 kilowatts, and there's a paper that's associated down there at the bottom if you're really into it, but you basically get 34 continuous values, and the 35th is the classification or the label that you're going to be using, and this is a binary classification task except for the clustering, which is unsupervised. So again, this is basically what your data looks like. Fairly straightforward features that end with 34, and then the label of good or bad. So to take a brief look through what this might look like, and yours could look quite different, and again don't assume that I'm showing you an A paper. So hopefully this installed, because before I started to run this, I found that this kernel doesn't have sklearn, and it looks as though it did. So then we basically want to read the data in and then do some exploration. So you want to do probably some stuff, not necessarily this, but you may want to do this. Describe is always useful, head's always useful. Knowing how many elements are in the data frame is useful, the number of columns, so basically the shape of it. However you want to do that, I'm just doing it one way. There's lots of ways to do that. You may want to take a look at the data types just as from a due diligence kind of sort of thing. And then maybe see what the distribution of the various labels are, and you can see that there's more good than bad, which is probably interesting. And then making sure that there's not something else other than good or bad. Then you're probably going to want to do a mapping to convert those from essentially categorical to numeric values. And that's all that's doing, is basically just creating using a target and pulling off the label and then getting rid of label after the fact. So I'm just replacing it essentially with G and B from G and B to 0 to 1. And then this is a handy piece of code that you may want to borrow, that basically goes through in all of the columns in the data frame, takes a look at it, prints out the name, the data type, if there are any null values inside of it, and if there are none, then you're good to go. If there are, then you would want to work on cleansing. You could get a similar concept here with the describe on the refined data set, but it's always a good idea to do an explicit test for nulls. Then you're probably going to want to do the splitting of the code. What I did here was slightly different. I basically wrote a function that you give it a classifier and a data frame, and it runs pretty much through the process, because it kind of seemed like that was the only thing that really different. And you can see I was experimenting. Some of this isn't really pretty because there's a lot of code in here that was left over. But with this, because I have that function, now I can basically create an instance of it and run it through and evaluate it in a single pass. And for some reason it's not printing anything out, probably because I commented out too much. But that gets you started, and I look forward to seeing your take on it. But that's basically it in a nutshell. Oh, that's why I didn't print anything out, because it's still running. So as always, if you have any questions, do feel free to let me know. That's what I'm here for. If there's a topic you'd like me to talk more about, something that we've brushed across, let me know. Otherwise, I might explore some other more interesting, related but yet tangentially so topics as well. So with that, I'll wrap this up. Feel free to shoot me an email, text, whatever, if you have any questions, and I'll talk with you on Wednesday.